In this video, we're going to talk about the method of substitution. The method of substitution is a technique which allows us, in some cases, to evaluate indefinite integrals. Finding derivatives is usually just a matter of applying a derivative rule. However, finding antiderivatives, or indefinite integrals, is usually a bit more subtle and requires some technique. The techniques that we're going to learn usually have their origin in some derivative rule, because every time you have a derivative rule, you're saying that something is the derivative of a function, and that function is the antiderivative, or the indefinite integral. In this video, we'll be talking about the method of substitution, which is one of the basic techniques used to evaluate indefinite integrals. The method of substitution has as its origin the chain rule. Let's just remind ourselves of exactly what the chain rule says. The chain rule is a rule for computing the derivative of a composition of functions. So suppose you wanted to compute the derivative with respect to x of a composition of functions, that is, a function of a function. So in this case, let's say that f is a function of g, which is a function of x. If we want to compute this derivative, we need to use the chain rule. That rule tells us that the derivative of the composition is the derivative of the outside times the derivative of the inside. The inside function is g of x. G of x also goes inside of f prime. G of x was inside of f, and then when you compute f prime, g of x is still inside. The inside function doesn't go anywhere, it's still inside. The only thing that changes is that instead of f, you have f prime. And then you have to multiply that by the derivative of whatever is inside your function. In this case, we have to multiply by the derivative of g. We can of course also write this as f prime of g of x times g prime of x, like so. This is a derivative rule. We want an integral rule, or at least an integral technique. And the origins of our technique is exactly what you see here. We have the chain rule telling us that the derivative of a composition is f prime times g prime. Well, f prime at g times g prime. So the derivative of the composition is given by this product, f prime times g prime. So what that means, if we turn this around, we get the following integral statement. And what does it tell us? It tells us, well, the chain rule says that the derivative of the composition is f prime times g prime. So that means the antiderivative of f prime of g times g prime dx, so the indefinite integral is the same as the antiderivative, or the general antiderivative, it's going to be equal to the original composition, f at g of x. Now, the indefinite integral is the general antiderivative. So for that I need a plus c at the end, where again c is the constant of integration. It's an arbitrary constant because the general antiderivative isn't just one function, it's a whole family of functions. You get a different function for each value of c. We call this an integral statement rather than an integral rule because it's not always apparent how to use this, at least not at first. What the integral statement is telling us is that if you have the integral of f prime of g times g prime dx, that's going to equal the composition f evaluated at gx plus a constant. But it's not always immediately obvious looking at an indefinite integral that it has this form. What we want to do is we want to change it in such a way that it becomes a little bit more obvious, or at least a little more apparent. And the way that we do that is by substituting. Instead of writing g of x, we're going to write something else. So the idea is to write u instead of g of x. That is, we're going to write u equals g of x. If we do that, then here we have f prime of u, and here we have f evaluated at u. What about this g prime of x? That's actually du dx. So if we rewrite this, we have the integral of f prime of u times du dx dx is equal to f at u plus c. Instead of writing du dx dx over here, we can replace that with du. Now, it might look a little bit like we're canceling out the dx's, but that's not actually what's happening. Du is what we call a differential, and the fact that du is equal to du dx dx is another way of phrasing the chain rule, but in terms of differentials. But for us, it's enough to just understand that these two quantities are the same. And that's very nice because that allows us to rewrite our integral as the indefinite integral of f prime of u du is equal to f of u plus c. So here we're using this fact, which we can then rewrite as du is equal to g prime of x dx. So when we're making our substitution at this stage, we can also compute the du in this way. So what does that do for us? Well, let's look at our new equation. The new equation says that the indefinite integral of f prime of u du is equal to f evaluated at u plus c. So in other words, the indefinite integral of f prime, which is the general antiderivative of f prime, is f plus c. But of course f is an antiderivative of f prime, and the general antiderivative of f prime is going to be f plus a constant of integration. So what we've done is simply rewritten the expression so that it looks as if it's saying to us the antiderivative of f prime is f plus a constant, of course. Now this is just simply the statement that f is the antiderivative of f prime, and this is definitely true. So what we've done is we've started with a statement which was a little bit complicated and perhaps not intuitive, and by replacing g of x with u, what we've actually done is rewritten the same equation, and indeed, this is the same equation. This is the same equation as before, but it's just more obvious to us or more apparent to us that it's a true statement. The idea being here that we are trying to discover the composition. We're going to start with an expression that looks like the integral of f prime g of x times g prime of x dx, but it won't look like that. The idea is that maybe it is this, and we can rewrite it in some way using a substitution so that it becomes something simpler, something that we know how to work with. Because what we're looking for is this antiderivative f composed with g. If we have f prime, we can then figure out what f is, and then in order to get the composition, you just plug in u equals g of x back into that expression, and you're done, or at least you have your answer. Notice that the key step is identifying u. What is u? Well, in terms of the chain rule, u is your inside function. You need to figure out what u is, the inside function, and then you need to compute du, which is the derivative of the inside function, times dx. So the key step is figuring out u. So u is the inside function. So you need to figure out what u is so that you can write the inside function as u, and the derivative of the inside function, g prime, that becomes your du. So when we start doing examples, that's going to be our main objective, to identify the inside function and call it u. So let's do an example now. We already have an example written down here for us. This is the first example that we're going to look at, the integral of sine of x squared times 2x dx. Now remember, our objective is to undo the chain rule. And in order to do that, we want to find our inside function and call it u. So u is going to be our g of x. And then du, remember, is the derivative g prime of x dx. So that's what we need to identify. So you want to look for the inside function in some composition. Let me just scroll back up to where we were looking at the chain rule. Here it is. Now, something that I mentioned when we computed the chain rule is something that's important now. When you compute the derivative of this composition, f evaluated at the inside function g, the first product is f prime times the inside function. So the thing that was inside is still inside, and you're also multiplying by the derivative, but importantly, your inside function is still an inside function. So let's go back to our example, and we want to look for a composition that has an inside function, and you can see one here. Sine of x squared, that's a composition, and the inside function is the x squared part. So I want to let u be equal to x squared. That's going to be my inside function. This only works if I can find the derivative of the inside function as well. It's not enough to have u. You also need your du, but du is basically the derivative of u. There's a dx here, as you can see. But u is equal to g, and du is g prime dx. So I need to find the derivative of my inside function. And I have that here. Because if u is x squared, then du is the derivative, which is 2x dx. And that's exactly what we have here, du. So this problem was set up in such a way that it was easy for us to find the pieces. The integral of sine of x squared is u du. And now we see the true value of the method of substitution. We started with an integral that was complicated, sine of x squared times 2x dx. And we've used this substitution by calling x squared u, and now we've reduced this integral, or we've rewritten this integral, so it's the same thing, but it looks a little simpler, because now we just need to find the antiderivative of sine of u, and that's something that we know. It's not cosine, it's the opposite of cosine of u, plus a constant of integration. Now at this point, it's very important that you don't forget to get rid of that u. The problem started with x's, so it needs to end with x's as well. So we need to put back in terms of the original variable, which in this case is x. Well, that's easy enough to do because we know that u is equal to x squared. So anytime you see a u, which is right here, you just simply have to plug back in x squared. So you end up with minus cosine of x squared plus a constant. And that's our general antiderivative. The great thing about computing antiderivatives is it's really easy to check. We can check to make sure that we have the right answer by computing the derivative of our result. Compute the derivative, the derivative of the answer. It needs to equal the original integrand. And this is something that we can do. So let's do that now. So let's check. In this case, we want to compute the derivative with respect to x of minus cosine of x quantity squared plus c. So this is going to be equal to minus the derivative with respect to x of cosine of x quantity squared plus the derivative with respect to x of c. Well, the derivative of a constant, whatever that constant happens to be, is 0. So that term doesn't come up. What about the derivative of cosine of x squared? Well, there's a minus sign in front of it. We don't want to forget that, so minus. And now we want to compute the derivative of cosine of x squared. That's a composition. We need to use the chain rule. And that shouldn't be a surprise because remember, the method of substitution started out as undoing the chain rule. Well, this is the chain rule in question. This is the chain rule that we're undoing. But now we're checking, so we have to compute this using the chain rule. The derivative of cosine is the opposite of sine of x squared. And then, of course, you have to multiply by the derivative of the inside. So the derivative of x squared. Well, minus a minus is plus, so then you have sine of x squared times the derivative of x squared is 2x. And if you compare that with what we started with, you can see that yes, indeed, the derivative of our answer gets us back our original integrand. And that's how we know we did it right. Let's do another example. So our last example was a, so let's call this example b. And this will be the indefinite integral of x e to the x squared dx. So here again, we want to identify this as being the result of a chain rule. And in order to do that, our main goal, at least at the start, is to identify the composition, identify the inside function. And there is indeed a composition here. It's the e to the x squared. The inside function is the x squared part. The outside function is the exponential. So the inside function here is x squared. So we're going to let u be equal to x squared. Now the other thing we need is the derivative, which is du. Du, well, u is x squared just like it was in the last example, so du is the derivative, 2x, and then you put dx afterwards. So in order for this to work, we need the inside function to be u, but we also need to multiply it by the derivative of the inside function. So we need to multiply it by 2x. Well, we almost have that. We have an x. Let me just rewrite this. So this is the integral e to the x squared times x dx. This is almost du. This e to the x squared is e to the u. However, x dx isn't quite what we're looking for. It's actually half of what we're looking for. What we really want is we want a 2 here. We want that to be 2x dx. And that's twice what we have. But that's okay, because if I put a little 1/2 in front of this indefinite integral, then I've multiplied by 2 to get double, but then I divided by 2 to get back to what we started. So what does that give us? What do we end up with here? We have 1/2 times the integral of e to the x squared times 2x dx. So the e to the x squared part is e to the u, and then the 2x dx is du. So we didn't have du, we had half of du. But it's fine to multiply by 2 so long as you divide by 2, because these are constants. So the constant, the 2, which is constant, you can take that out of the integral and it would divide with the other 2. So that's fine. But now what this means is we have the integral of 1/2, well, 1/2 times the integral of e to the u du. And now we just need to ask ourselves, what is the antiderivative of e to the u? Well, we have a 1/2 in front, and then the antiderivative of e to the u is e to the u, or an antiderivative. And then we just have to remember to add in a plus c. The c is the constant of integration. So now we've computed our indefinite integral, at least in terms of u, but we have to get back into terms of our original variable, which is x. So we need to just use again the fact that u is equal to x squared, and we just plug that back right into where we see a u, which is right there. So we're going to end up with 1/2 e to the x squared plus a constant. And that's our antiderivative. Again, we can check this just to be sure that we have the right answer. So the derivative with respect to x of 1/2 e to the x squared plus c. Well, just like always, that plus c is going to go away. The derivative of a constant is 0. So this is just going to be 1/2 times the derivative with respect to x of e to the x squared. This is a composition, so we have to use the chain rule. Again, we shouldn't be surprised that we have to use the chain rule because, remember, substitution is basically undoing the chain rule. And the chain rule in this example is e to the x squared. So let's compute that. The derivative of e to the something is e to that same thing. Then you have to multiply by the derivative of whatever that thing inside was. Now the derivative of x squared, of course, is 2x. So what do we end up with? We end up with 1/2 e to the x squared times 2x, and the 2 and the 1/2 cancel. So we just end up with e to the x squared times x, which is what we started with. Well, we started with x times e to the x squared, but it's all right if I write it on the other side. These two things are equal. This is equal to x times e to the x squared. So our answer was 1/2 e to the x squared plus a constant of integration. And if you differentiate your answer, you get back your original integrand. So that means you have the right answer. Let's do one more example. This time, let's do a definite integral. Let's do the definite integral from 2 to 3 of x squared times the square root of x cubed plus 1 dx. So here we have a definite integral. One way to think about definite integrals one way to solve definite integrals rather, is to first find the antiderivative and use the evaluation theorem. And you can find the antiderivative using the method of substitution. However, another way to approach this is to convert the entire problem in terms of a new variable. Let's make that clear by doing an example, namely this example. The first thing to do is try to figure out what your inside function is. And the hint here is that it's inside something, quite literally in the sense that it's inside a radical. So our inside function is inside a radical. So we're going to let u be equal to x cubed plus 1. In order for substitution to work, it's not enough to have an inside function. You also have to have the derivative, du, or at least a constant multiple of the derivative. So in this case, we have for du 3x squared dx. And we don't have a 3x squared, but we do have an x squared. So that's almost what we're looking for. Let me just rewrite this again, like before. The definite integral from 2 to 3, and I'm going to write this as x cubed plus 1 raised to the 1/2 power times, and then we have x squared dx. Notice I left a little space there, and I left that little space because I need a 3. I don't currently have a 3, but I'm allowed to add a 3 here. I say add, but I'm multiplying by 3 because that's a constant. Multiplying by 3 gives me something that's 3 times what I actually have, so I have to put a 1/3 out in front. Just like before with the 2 and the 1/2, this 3 comes out and cancels. So it's all right if you multiply by something, so long as that thing you're multiplying by is a constant. So now we have x cubed plus 1 to the 1/2, that's u to the 1/2. And then our 3x squared dx, that's our du. So what does that tell us? That tells us we have 1/3 times a definite integral. let's talk about the limits of integration in a second. The first thing we're going to do is we're going to write this as u to the 1/2 du. Now, one thing I cannot do is I cannot simply write 2 to 3 for this definite integral. Now, why is that? When you see this definite integral from 2 to 3, this is telling us that the x values go from 2 to 3. Imagine that this dx is an instruction, and it's telling you to essentially sum or integrate over the x values. And you start at 2 and you climb up the integral symbol until you get to 3. So x starts at 2 and climbs up to 3. So we have that x is always between 2 and 3. So I can't put 2 down here and 3 down here because now I'm talking about u's. I need to know where the u's go. And how am I going to figure out what the smallest u is and the largest u is? I know what the smallest x is, it's 2. And I know what the largest x is, that's 3. So how can I use this to figure out what the smallest u is and the largest u? So I need to figure out what goes here and what goes here. I need to figure out what goes into those boxes. Instead of me putting a box there, let me put a triangle. So the box goes down at the bottom of the limit of integration and the triangle goes up at the top. And I just need to figure out what numbers go there. Okay, how am I going to do that? I know what the x values are. The smallest x is x equals 2. And the largest x is x equals 3. Well, how can I figure out what u is based on this information? Well, fortunately, I have this formula right here that tells me what u is in terms of x. So if x is equal to 2, then u is equal to 2 cubed plus 1, which is 8 plus 1 is 9. For the largest value of x, I have x equals 3. So if x is equal to 3, then u is equal to 8, not 8, u is equal to 3 cubed plus 1, which is 28. So that tells me that the 2 corresponds to u equals 9, and the x equals 3 corresponds to u equals 28. So I can put a 9 here and a 28 in that triangle. Now it's a little hard to read that, so let's rewrite it. 1/3 times the integral from 9 to 28 of u to the 1/2 du. Okay, now this is a definite integral, and here we have u between 9 and 28. And that's what this definite integral means here. We're integrating with respect to u, and we're going from 9 up to 28. Okay, so how do we do this? Well, this is u to a power, so we can integrate that. We increase the exponent by 1, so it becomes 3/2. And then you divide by that exponent, 3/2. And you're going to evaluate from between u is equal to 9 and u equal to 28. So 1/3 times dividing by 3/2 is the same as multiplying by 2/3, u to the 3/2 between 9 and 28. So this is 2 over 9 times 28 to the 3/2 minus 9 to the 3/2. And that's our answer. Now notice I didn't end up with an antiderivative here. That's because I'm looking at a definite integral. Importantly, I don't have to convert back to x's because when you compute a definite integral, all of your variables go away. There is no x here anymore. There's no x at this point. Once you convert everything into u, we've even converted the limits of integration into u. And because we've converted the limits of integration into u, we don't have to go back to x. The other thing that we could do if we wanted, so note, if we want, we can evaluate the original definite integral which is the integral from 2 to 3 x squared times the square root of x cubed plus 1 dx, by first finding an antiderivative. For x squared times the square root of x cubed plus 1. And then using the evaluation theorem. That is to say, the definite integral from 2 to 3 of x squared times the square root of x cubed plus 1 dx can be evaluated by first looking at the indefinite integral from x squared times the square root of x cubed plus 1 dx, and then whatever that happens to be, looking at the net change between x equals 2 and x equals 3. And you can use substitution to find this. So we can use substitution to evaluate that, and that will give us a function of x. You'll have to use substitution first, so you'll have the integral from x squared square root of x cubed plus 1 dx. So of course we do the same substitution, u equals x cubed plus 1, du equals 3x squared dx. So then this is the integral, square root x cubed plus 1, which I'll write as x cubed plus 1 to the 1/2, times, and then again x squared dx. I write the 3 there and a 1/3 in front, and now this is u to the 1/2 times du. So we have 1/3 times the indefinite integral of u to the 1/2 du. And this is something that we can evaluate. So it's 1/3 times u to the 3/2 over 3/2, just like before, but now it's an indefinite integral. So we have a plus c, which is 2/9, just like it was before, u to the 3/2 plus c. But doing it this way, we're trying to find an antiderivative for our function of x. So now I need to take this u and plug it back into our expression here. And so we end up with 2/9 times x cubed plus 1 to the 3/2 plus c. And this is our antiderivative. So what we can do instead is we can write the integral from 2 to 3 of x squared times the square root of x cubed plus 1 dx is equal to an antiderivative, 2/9 times x cubed plus 1 to the 3/2 plus a constant, but we can choose whatever constant we need for the evaluation theorem, because the evaluation theorem will work for any antiderivative. So we can choose the one where c is equal to 0. And then we evaluate that at x equals 2 and x equals 3. So here I'm using the evaluation theorem. And what happens if you actually plug this in? You're going to have 2/9 times, well, if you plug in 3 into here, what are you going to end up with? You're going to end up with 3 cubed, which is 27, plus 1 is 28 to the 3/2, minus 2/9 times, and now we plug in 2 into here, and we get 2 cubed is 8, plus 1 is 9 to the 3/2. And notice, what is that? That's the same thing that we had before. That's the same thing that we have here. So it doesn't matter how you do it, you can do it either way, and you'll end up with the same answer.